Hey kiddos, Module 22.2, Independent Events. Our essential question is what does it mean for two events to be independent? Shortest answer possible is two events are independent provided that the occurrence of one event has no effect, again, has no effect of the occurrence of the other event. Okay, so for example, if you have a whole bunch of meat options at a buffet, right? You're trying to pick all the meat. You notice there's one more ribeye on the plate or on the platter, and you grab it. And then the person behind you, well, they're going to grab something that's on the platter as well. But then they suddenly realize, wait, I'm vegan and I don't want meat. So whatever you just did with grabbing that last ribeye has no effect on their decision for what they want to eat. They're going to go over and pick a nice piece of kale or salad, something that rabbits eat. Okay, so again, those are two independent events. One outcome has no bearing or effect on the other event. Okay, so for independent events, we'll call them A and B. The probability of A given B should equal the probability of A. B doesn't have an impact. So basically, the probability of event A does not change even when event B is assumed to have occurred. All right. So understanding independence of events. Now, suppose you flip a coin. All right. So you got a coin. All right. You flip it. There's a 1 out of 2 chance you're going to get heads or tails, right? And you happen to roll a cube. All right, a dice. Now, whatever you get on uh, your coin, it's not going to have any effect on what you get for your cube. So your cube, you have a 1 out of 6 chance of getting a certain side, but the coin is 1 out of 2. But they are independent. They have no correlation to one another. They are two separate items. Okay, for example, a meat eater or omnivore. Actually, let's say meat eater, and let's stay as far independent as possible. The meat eater has no correlation, no connection to the vegan. All right, that doesn't affect them. So the dice has no effect on the coin. That is independent. All right. So when the occurrence, this is the definition, when the occurrence of one event has no effect on the occurrence of another event, the two events are called independent events. All right. So let's look at an example. Example A, or example one. A jar contains 15 red marbles and 17 yellow marbles. Now, real quick, sample space. We realize there's 32 marbles, right? Because 15 plus the 17 yellow marbles gives us the sample set, which is 32. All right, so what's the probability of us pulling out a red marble? Well, how many reds do we have for that event? So we have 15 red out of the 32, and the probability of our yellow is 17 yellow marbles out of the 32 total. So those are our probabilities for those two separate events. Now, suppose the first marble I draw is red, and you put that marble back in the jar before randomly drawing a second marble. Ooh, that's really important to note. Okay, that does change our outcome for our second event. Now, to find the probability of pulling out a yellow marble, given that it's red, the probability that you get a yellow marble on the second draw after getting a red marble on the first draw, we have to explain what this is. So, out of the total of 32 marbles, and 17 are yellow, well, if you get a red marble, the first one, you put it back in the bag, it doesn't change anything. You're still going to have 32 marbles total, especially if you put that red right on your pick. If you put it back in the bag, so it doesn't matter. It doesn't change your sample set, and the probability, if you notice, is going to be the same as it was earlier. So that's kind of a cough cough. This is like what it means to be independent. All right. All right, so let's see. Part C. Suppose you don't put the red marble back. Okay, now we're getting a little bit more interesting. Now we have to find the probability that we're drawing a yellow, given that we drew a red first. Okay, so the probability you get a yellow marble on the second draw after getting a red marble is going to be down below. So we have, well, if you don't put the one red marble back, you're no longer going to have 32 marbles. You're going to only have 31 marbles, right? Because we did not put the red back. All right, but we still have 17 yellow. So 17 yellows out of, well, how many are our sample space? 31. So notice how drawing the red marble and not putting it back does affect the probability for drawing a Y. So notice the difference between independent and dependent right there. Okay, so let's look at the next example, determining if events are independent. So we got a two-way frequency table that gives us data about 180 peeps, all right, 180 people. Selected to arrive at an airport. Let's start with part A. Is the event that a flight is on time independent of the event that a flight is domestic? Okay, so let O be the event the flight is on time. So we got on time. All right, that's O, event O. And let D be the event the flight is domestic. All right, so D is domestic flights. Now find the probability of on-time events and the probability of on-time events given that it's domestic. So to find the probability of on-time, note the total number of flights is 180. So again, that's our sample space, something to be important about there. And then of those flights, there are 162, right, for event O. So we should have the probability of O equaling 162 divided by 180, which is about 90%. Now that's just for the probability of O. Now what about the probability for on time, but given that it's domestic? So we have, please note that we have a total of 120 for domestic, so N of D, okay, that's important. And of those flights, 108 are on time, right? So we basically have the probability here. We got 108, right, out of the total 180. But of those, we have 120 that are domestic out of 180. And again, the 180s cancel out, and you just get this lovely little number right there. All right, so 90% are on time given that they're domestic. International flights take a little bit more approximation for when the arrivals are going to get there, right? All right, so the probability of O given that it's D equals probability of O. If you actually notice, these guys are the same. All right, very nice, very nice. All right, so the event that the flight is on time is independent of the event the flight is domestic. So again, if they equal one another, if probability of O given D equals the probability of O in the first place, those two events are independent. All right, so let's take a look at part B. Is the event of a flight international independent of the event the arrival's flight arrives late? So let me go ahead and clean up our table here so we can focus on what key items we have to look at. All right, so we have international flights, right? We'll call that I, and late we'll call event L. All right, so here we go. First, again, we have to find the probability of international, and international flights total, right, will be our sample set, or I'm sorry, our number of elements in that event, which is 60 out of 180. And then our lates are 18, so our numbers for L. And again, we're still using the same sample space. So again, there are 60 international flights, right, from up here. And then, so the probability of international is really just 60 out of the 180. You can reduce, and you get 33.3%, really. So, or one third. So 33.33%, a third. Okay. Um, will be late. Now, to find the probability of I, given that they're late, or international, given that they're late, we have to note that there are 18 flights, right, that arrive late. And of those flights, how many of them, of those flights were international flights? And if we notice, the intersection between event I and event L is 6. So that's something to note. So we're going to have the probability of international, given that it's late, it's going to be really just 6 out of 18, which is also going to be 33.3%. Okay. So since these guys are equal, right, the event of the flight international is going to be independent of the event the flight arrives late. Okay. So that's what they're trying to say is those two events, whether it's international or it's late, they're independent from the domestic. Okay, the domestic doesn't have an impact on all that stuff, so that's why those are independent. It's like why is your plane late? Oh, because the one plane that I didn't take was on time. It's like what? It has nothing to do with that. All right, so your turn number one. Two-way frequency table again. And what you're going to do here is, let's see, we got one bedroom, two plus bedrooms, single occupants. Okay, let's see. Let's look at the first question. Is the event of the apartment that has a single occupant independent from the event that the apartment has one bedroom? So let's see. Single, we'll call that event S, and apartment is one bed. We'll just say group event one. Okay, will be the one bedroom. Um, one thing to consider again is what's the probability of being a single occupant, and what is the probability of one bedroom, and we need to consider how we're going to set this up. So let's see here. We got the probability that you are a single occupant, given that it's one bedroom. All right. So you have to see if that equals the probability of being a single occupant. Now, again, if they're equal, they are independent. If they are not equal, they are not independent. And again, pay attention to what your sample space is. All right. Same concept with this question down here, except basically what you're trying to do here is you're trying to find the event the apartment has two or more bedrooms are being independent from the event that the apartment has multiple occupants. So again, you're doing the probability of two beds, and I'll say this event is two, given that it is multiple occupants. We'll call that M. Okay, that's at the event, and that should equal the probability of having two bedrooms. So again, if they equal each other, they're independent. If they do not equal each other, they are if they do equal each other, independent. If they don't, not independent. All right, finding the probability of independent events. From the definition of conditional probability, and we've talked about this, note that the probability of A given B equals the intersection, or the probability of the intersection of A and B, divided by the probability of event B occurring for both events. Now, if those events happen to be independent, you can replace the probability of A given B with probability of A and get this. That's nice to know. Note, solving the last equation for the intersection, the probability of the intersection for those two events. So the main thing to notice again is the probability of the intersection of A and B should equal the probability of A times the probability of B. That's like the main idea right there. Like definitely box that. Okay, that's the main idea for most of the homework too. All right, so example two, we're going to find the specified probability. Now, we're going back to the marbles. Okay, we got 15 red marbles, 17 yellow marbles from that explorer that we just previously did in the beginning. Now, suppose we randomly draw one marble from the jar. After you put that marble back into the jar, okay, so we're putting it back, you randomly draw a second marble. What is the probability that you draw a yellow marble first and a red marble second? Okay, so let Y be the event of drawing a yellow marble. Let R being, drawing that you drew a red marble. And the probability of Y is still going to be 17 out of 32. And because the first marble drawn is replaced before the second marble is drawn, okay, it's going to be conditional where the probability of drawing a red, given that your first draw was a yellow, should equal the probability of drawing an R, or a red marble, which is going to be 15 out of 32. Now, what we're going to realize here is since they're independent, okay, since again the probability of R given Y equals the probability of R, you can multiply their probabilities. So the intersection that you have, the probability of Y intersecting with the event R, should equal the probability of Y times the probability of R. Now, again, what you can do here is probability of Y was 17 out of 32 times the probability of R, which was 15 out of 32. And you get this huge number, right? Numerators times numerators, denominators times denominators. And that's approximately 25%. All right, so if you are trying to figure out what are we comparing this to? Again, probability of drawing a red, given that it's Y, was the first one. You could always talk about, well, um, you know what? I don't want to give you that one. I want you guys to try to discuss where did the 25% come from? Yeah, it came from here. It came from multiplying these two. But how else could you have shown this? So I want you guys to talk to each other about this and try to see how those equal each other. Because how does the probability of Y intersecting R equal 25%? Okay, so figure that out for me. All right. Figure out how you can get 25% there. All right, example 3. So find the specified probability. So this is a part of the same concept. We spin a spinner, shown 2 times. Okay, so we spin this thing twice. That's important to note. What is the probability that the spinner stops on an even number on the first spin, followed by an odd number on the second spin? Ooh, that's a good one. All right. Let E, so we're starting off there. Let E be the event of getting an even number on the first spin. Let O be the event of getting an odd number on the second spin. All right, so O, E, ooh, ah, ah, ting, tang. All right, there we go, and an odd, okay. So the probability of getting an even number, well, how many even numbers do we have? All right, so even numbers, let's see. Thank you, little pin. We have what? 2, 4. Whoa, where's a 2? Do you guys see a 2 there? I don't see a 2. It's like 1, 3. It's just random numbers. They almost got me there. All right, so how many even numbers do we have? We have 6, right? We have 8 and 12. Wow. Okay, so number of elements in event E is just 3. Our sample space is out of how many numbers? 8, right? So we got probability of getting an even. That's going to be 3 out of 8. And because the first spin has no effect on the second spin, right? Because you're still using that same number. You could get the same number twice for all we know, right? Has no effect on the second spin, all right, which kind of claims independence. We have the probability of O given E should equal the probability of O, okay, which is, again, how many odd numbers do we have? All right, so if we look here, odd numbers, how many odds do we have? 1, 2, okay, I'll write them out. We have 1, 3, right? Odd numbers. We have 5, 7, and 9. We have 5 in event O. And that's 5 out of 8. Now, since the events are independent, again, the first spin doesn't mess up your second spin. It's independent, just physically, okay? You can multiply their probabilities. So, again, the intersection of E and O should equal the probability of E times the probability of O. So you basically just have 3/8 times 5/8, and you should get 15 over 64. And in your calculator real quick, you should get 23%. All right. So again, go ahead and find me the probability of E intersecting O. This is kind of conversation hopefully you had last example, and see if you actually get 23%. All right, so show me that. Show me if you actually got 23% to kind of verify what they're saying here. All right, your turn number 2. Basically, here we go. We have a spin on a spinner with 4 red sections, 3 blue sections, 2 green sections, 1 yellow section. If all those sections are equal size, that's very important. What is the probability that the spinner stops on a green first and a blue on the second? Well, first things first is we have to figure out the probability of your spins. So um, let's see. Green, right? Green first. So we actually have to figure out the probability of green first. Then we actually have to figure out the probability of, let's think, the probability of blue is going to be nice. Now, does the first spin affect the second spin? No, they're independent. So the probability of you rolling and again, second roll is a blue. Now, what's the probability of getting a blue given that your first one was green? Well, that should be independent from rolling the green. So it should be equal to the probability of rolling the blue. So what is the probability of rolling a blue, right? You have 4 red sections, 3 blue sections, 2 green, and 1 yellow. How many sections is that total? And that's going to lead to your sample space. All right, so go ahead and try to figure that out. Find the probability of blue, and then you should realize that hopefully, if you do this correctly, the probability of green intersecting the blue should be equal to the probability that you pick event G times the probability that you get event where you draw the blue. Go ahead and try that, see what you guys get, and let me know. All right, example 4, showing that the events are independent. So more examples, more the merrier, I say. Can never have enough. A two-way frequency table. So we got 120 randomly selected patients. Take vitamins, no vitamins, regular exercise, no exercise. Okay, so one thing to notice, we are determining whether these are independent events. So let V be the event where the patient takes vitamins. Okay, that's event V. Let E be the event that the patient exercises regularly. Okay, exercise. Find the probability of V. Okay, well, let's see. Vitamins is what? We have 60 people out of 120. So the probability of taking vitamins is basically 1 out of 2. All right. Find the probability of, let's see, E. Okay, so that's important to note. Weird. Did they just, ooh, did I catch a typo? It's a typo. Where'd they get B from? It's a typo. Woo! Typo. Ding ding. Hopefully I get a Scooby snack after I tell all the other teachers about this book. It's a good book. I'm not hating on it. It's just that's a typo. All right. Super excited about that. All right, so we had 76 people get regular exercise out of, again, our whole sample space. So the probability of getting exercise, regular exercise, is really just 19 out of 30. All right, we had 76 out of 120. We can reduce. All right. then we have to find the intersection, the probability of you getting taking vitamins um, and regular exercise. And hopefully you realize the intersection is just right there. It's just 48 out of 120, which is 40%. Um, Interesting. So comparing this idea that we have the probability of the intersection of event V and E, it should equal the probability of vitamins times the probability of regular exercise. But what we notice here is we had 40% here, but when we multiply probability of E and V, we get like 32%. Okay, those guys aren't the same. Okay, that means the probability of the intersection of vitamins and regular exercise does not equal the probability of vitamins times the probability of regular exercise. So these events are not independent. So you can totally check real quick because remember on the last couple examples, I'm like, what's the intersection? You know, like show me. That's what I kind of wanted you guys to like talk about, and hopefully you guys did that, and you guys got kind of this idea going. All right, so showing that events are independent, another example, this time a little more fill in the blankish, but we're still working with the two-way frequency table. So again, we have to find the probability of, well, let's see let B be the event, the child knows how to ride a bike. All right, knows how to ride a bike. There we go, that's our event B. Let S be the event the child knows how to swim. Okay, knows how to swim. Got it. All right, so first we have to find the probability of the kid knows how to ride a bike, which we have what 45 kids. So there are 45 kids who know total how to ride a bike, and well, of those 45, out of what 60 kids, so we can actually reduce, and we get 3 out of 4. So 3 out of 4 kids know how to ride a bike. Sweet. Now, what about the probability that they know how to swim? Well, we got 40 kids here who know how to swim, and that's still out of our sample set, which is 60. And we could reduce, and you get 2/3. So 2/3 out of these kids know how to swim. All right. Now, what about the intersection? The probability that they know how to ride a bike and they know how to swim. And the table shows the intersection right there. So we got 30 kids who know how to do both. That's 30 out of 60, which is really just 1/2. Now, again, what we're trying to do here is we're trying to see that if the intersection equals the two probabilities multiplying to each other. So the probability of B, okay, again, which was 3/4, times the probability of S is 2/3, and that should equal, again, 1/2, but does it? We get 6 times 12, right? The 3 times 2 and the 4 times 3, which if we reduce is 1/2. And that basically means that these two guys are equal to one another. And that is good in the sense that if they are equal to each other, there we go. If these guys are equal to each other, then that these two events are independent. Okay, so um, if the kid knows how to swim, it doesn't affect whether or not they know how to bike. They're independent from each other. All right. So let's see. Gertrude number 3, same concept as before. Look at your sample space. Let's see what events they're talking about. A student wants to know if a right-handed person are more likely to play a musical instrument than a left-handed person. Okay, that's interesting to note. Again, data collection is out of 250 people. Determine whether right-handed and playing musical instruments are independent events. And playing music, okay, so we're trying to figure out if right-handed even matters when playing musical instruments. Okay, so let's take a look here. What is the probability of being a right-handy? Okay, so that's the event R. What is the event, all right, that we care about? What is it? Musical instruments, right? So we'll call that event I. And then what is the probability of the intersection of being right-handed and um, playing instruments. So again, see if this, the intersection of being right-handed and playing an instrument, equals the probability of being a right-handed person times the probability of playing an instrument. If they equal each other, they are independent. If they are not equaling each other, they are not independent. All right, so there's your homework. If you have any questions, come see me. And that is it. And that guy is definitely thirsty.